Okay, welcome everybody. I think we're online on stage again. Thanks everybody for joining again to our conference. We are going to have our last talk for today by Claire. But before I introduce Claire, I still wanted to let you know about the technical details for those of you who are new to the conference. We typically have the talk in one piece, and then if you want to ask a question, please use the box Ask a Question and type your question in there. For the ones who moderate the session, it's very helpful if you in fact do ask questions and do it also early so we can monitor the questions. Everybody else can also vote questions, like upvote questions and like questions, so I know which are the questions that most of you would like me to ask in the end. So I'd be glad if you help me doing that. And with that, I would like to start and welcome Claire Monteleoni to our conference. Claire, I've known her almost, it feels like forever. We've done our PhDs at the same time. We have shared rooms at conferences. We had lots of great experiences jointly. So it's really my big pleasure to have her talking at our conference. Claire has been at many different places. She's been at MIT, UCSD, Columbia, George Washington University, and now she's at the University of Colorado. And the reason why we invited her to the conference is that her research, I mean, on the one side, she did a lot of research in learning theory, but she also has this other branch of research, which is it's called climate informatics, and it tries to combine machine learning with some questions that are relevant for today's society, like climate or sustainability. And this is, I think, a very interesting area, in particular for our research cluster in Tübingen. And today, Claire is going to talk about deep unsupervised learning for climate informatics. So Claire, thanks for joining.
Thanks so much for the kind introduction, Ule, and it's great to be here. I'm actually in Boulder, but luckily I've visited Tübingen, and I know that it's a beautiful place, so thanks for inviting me. So we study climate informatics due to the threat of climate change and the extreme events such as megastorms and heat waves resulting in wildfire and drought, and their effects on communities and ecosystems. Machine learning, climate informatics is based on the vision that machine learning can shed light on climate change. And we have some critical mass working in this area where we bring in all walks of data science, so AI, machine learning, statistics, data mining, with all areas of climate science and the study of climate change. And we've been doing this for about a decade, and actually our 10th conference is happening this year in Oxford, but actually virtually in late September if you want to come join us. And we also do a hackathon on a climate informatics challenge problem. So speaking to NeurIPS, one of the top meetings in machine learning about 6 years ago, Arindam Banerjee and I tried to increase interest in machine learning researchers in climate change problems. And it's sort of like the early days of bioinformatics, where all you can do is paint in broad strokes where you think machine learning may have an impact, but we're really just scratching the surface. But at least back then, the way we sort of broke down the world in terms of where machine learning had made an impact or could make an impact were problems of paleo climate reconstruction. So understanding past climates when you really only have some proxy data from measuring ice cores and tree rings and other proxies, which are extremely sparse over both time and location. In green are some of the topics that my lab has worked on. Today, I'm probably only going to have time to talk about climate downscaling, so I'll get to that shortly. But we've also had a big thrust on how to reduce uncertainty on predictions of future climates when you have these physics-driven climate models from all different countries that have really high variance over the different models as to their future predictions. All of these problems in climate informatics have a spatiotemporal component with a lot of interesting dependencies over both space and time. We'll see that a little bit today. And then I'll mention at the end some of the work we're doing around extreme events such as hurricane track forecasting and other problems, but this is a large area of uncertainty. So even though there's a consensus among climate scientists that there's a warming trend, that's talking about on average, and understanding what's going to happen at the extremes or in the tails is highly uncertain. So if you're a scientist and you don't see one of your problems on this list, I want to assure you that machine learning can still have an impact on your problem, and we're just scratching the surface here. But it would be great if within Tübingen, machine learners could seek out people in these environmental and climate areas to work on collaborations. So what I have time to do in this 30-minute workshop session is focus on how some recent methods coming out of the field of unsupervised deep learning can be useful in climate informatics. Sort of in the longer version of this talk, I would have 2 case studies, one on avalanche detection, which I probably won't have time to talk about. I'm mostly going to talk about downscaling of temperature and precipitation. And in that context, not only are we going to talk about unsupervised learning, but also a little bit about the idea of self-supervised learning. So I usually kind of give talks with like a punchline first, or maybe a more advanced statement front-loaded. That said, if this slide does not make sense to you, don't worry, we're going to motivate everything through a case study. But for those of you familiar with training a supervised deep learning network, we can just view it as our network parameters W are going to be trained by doing gradient descent, basically trying to minimize some prediction loss function, where prediction loss takes the output y hat of the network on some input data point X and compares it to some true label or some true target output for that particular data point X, so that label Y. So maybe you have some spatiotemporal data field and you're trying to forecast temperature maybe a month in advance, so your output is a scalar temperature value. Maybe then if you just have scalars, your loss function will be y hat minus y squared, where y is the true temperature that you're trying to forecast if you had ground truth knowledge of that. But the point here is just that to update all the parameters on your network, no matter your architecture, you're going to take gradient descent steps on this loss function, and then via the chain rule that'll tell us just the incremental updates to each network parameter in the entire network, which I'm representing as capital W. So if that model makes sense to you and you're already familiar with this, then I'm trying to demonstrate how simple it is to go from the supervised deep learning framework to the unsupervised deep learning framework. And you might need to do this in the case where you don't actually have a ground truth label for your data point X. But really, the setup is quite similar. I'm still going to call for whatever architecture. Still going to call all my network parameters, the edge weights in my network, this set capital W. I'm now going to denote the output of the network X hat. And since I don't have a label Y, I can write down some loss function, but of course it can't depend on some external information Y, some label for the data point X. So it's only allowed to depend on the network's input X, as well as the network's output X hat. But this is meant to seem very simple because training the unsupervised deep network now just amounts to doing gradient descent now on this loss function, and still, using the chain rule, we'll get our incremental updates for every network parameter W. So this should hopefully be very freeing for you if you're a practitioner that does not have a lot of ground truth data paired with the target label for that data. You just have a lot of sort of raw data. And I'm mostly going to be talking about this in terms of embedding or dimensionality reduction. That's the rest of the talk. But I did want to mention that if you think about learning on mini batches of data points X, then it would also make sense to write down clustering loss functions here, since clustering loss functions only depend on the training data. And then we can optimize those. And so I'll point you to a paper called SpectralNet that is essentially doing spectral clustering without the spectral clustering. You write down a spectral clustering objective, and then you just optimize some network parameters to try to minimize that. Okay, so I think this is a really exciting field, and especially since we're talking now to scientists that might not always have Y labels, you might want to consider unsupervised learning and unsupervised deep learning in particular. Okay, when we talk about embedding or dimensionality reduction, the first thing we probably talk about is an autoencoder. And this seems like a very stupid machine. The goal of this machine is given some input. So here's a grayscale image of grayscale pixels that was probably the result of a human trying to write the number 2. But as far as the machine is concerned, we're just trying to reconstruct a similar image as the output. In the encoder and decoder, these are just networks where we're going to fit weights. This machine is not that helpful because all it does is, given some kind of input, it tries to output something very, very similar. But we call this basically a pretext task because while training on many images where we're trying to output something very similar to the image, and then fitting these weights, we'll get some kind of latent representation that should represent all the training data point in some latent space. And usually we will think of this as a compressed representation, because if we're sending this through a bottleneck that's lower dimension, then we're going to have a lower dimensional representation than this original pixel map. And that's typically how vanilla autoencoders are thought of. So the input dimension will be larger than the bottleneck dimension, and so we get dimensionality reduction. That said, and I know there's good cognitive science going on at Tübingen, you could also take this through a larger dimensional, what we call a wide layer, meaning the dimension of the middle layer is larger than the input layer. And that's good if you want to now project to a higher dimensional space and then have sparse encodings of your signal, which has been shown to be true for the olfactory system of the fruit fly and is conjectured to be true for the human visual system. But I think in science, where we maybe have a very high dimensional input and just want to have a compressed representation, it's perfectly fine to think about this bottleneck as compact. So that would be a dense autoencoder. And then the one step in going from just a vanilla autoencoder to a variational autoencoder is that we actually would like to have a probability distribution over a latent space instead of just one latent representation. And so VAE was typically introduced with a Gaussian representation where you might initialize with some isotropic Gaussian, but then you would learn your parameters for the mean vector and for your covariant structure while you're learning the autoencoder. Okay, and sort of the punchline of where we're going in this talk is we're going to talk about some very recent work using normalizing flows where we don't have to be limited to the Gaussian. That said, we're not going to be using an autoencoder, so we're going to skip the encoding and decoding layers. Okay, and in terms of what my group is really excited about unsupervised deep learning, and we have a few projects, but I'm only going to have time to talk about the downscaling task, so the second task, but maybe in the question session, I'd be happy to talk about the avalanche detection task. So this is an unsupervised deep learning approach applied to a problem in climate informatics that I'll explain shortly. And my interpretation of why it works so well is due to a self-supervisory interpretation. Okay, so Brian Gronke, who actually just moved to Germany to start his PhD in climate group in Potsdam, recently did his thesis with us along with a startup here in Boulder. And he was interested in the problem of downscaling. And I think when we get a lot of people from different fields into the same room, we have to be careful with terminology because down versus up is different, how it's used in climate versus in machine learning. So what we're saying is that we have some coarse scaled grid of data, maybe a temperature map at a very coarse scale, and we would like to infer the values at finer scales. So computer vision or AI people in the meeting might think, okay, great, let's just use super resolution techniques from computer vision. Well, he spent all summer with his internship at Jupyter Intelligence trying to use supervised techniques for super resolution. And he concluded that it's really not the best match because we have increasingly finer and finer scales of physical signal when we're looking at these fluid problems, such as climate meteorology. And it's not a simple in-painting task, and he couldn't get the super resolution techniques to work as well as this ultimate approach with unsupervised learning. So downscaling is a problem in climate meteorology, and it's addressed by the field of statistical downscaling. From a machine learning interpretation, these are supervised learning methods. And what we mean by that is if you want to fit a model, most of the statistical downscaling models from data, you'll need paired data. So you'll have your temperature map at the coarse resolution paired with the target temperature map at fine resolution. You need a lot of such pairs. So that's what we would call labeled data or supervised learning to train the methods. And then we also found that the literature mostly focused on models that would provide point predictions. And what we mean by that is after we have trained the model on paired data, we can query it, right, by sending in, say, temperature map at coarse scale, and the model will output one temperature map at fine scale. So we'll call that 1 point. But we were actually interested in outputting a distribution over such maps at the finer scale. And in AI, we would call that a generative model, learning a generative model. So Brian wanted to address generative downscaling, which is, to our understanding, an open problem in the field. And so he appealed to this task of domain alignment in machine learning, which allowed him then to use some bleeding edge methods. So the main method came out at this year's AAAI to address domain alignment. I'll get into that shortly. The method does need a normalizing flow, and for that we used GLOW. But again, sort of front loading the punchlines, if you want to understand why this worked well, I mean, I think these are great methods coming out of the AI literature. And also, they were aided by the fact that the input data that we used, even though our coarse-grained resolution data and our fine-grained resolution data were actually generated by completely different processes, they were both aligned over the same larger bounding box over the continental US. And so there is some shared underlying structure that then the AI methods can reveal. And so putting those together, he obtained a generative model for downscaling. So as I mentioned, the data types have different sort of origins. One is reanalysis data, so that's can be mostly viewed as observation data, but then fed through a physics-driven model to basically provide some sort of smoothing. So we'll call that our ERA data set, which is our coarse-grained data set, meaning it's at 1 degree latitude and longitude grid box resolution. And we did one task on temperature and one task on precipitation. For the fine-grained, we used the output of NWP, numerical weather prediction systems, in particular the WRF system, giving us data at 1/8 degree lat-long grid box resolution. And again, we had both temperature and precipitation. So domain alignment in machine learning is the task where you assume that you have two random variables for which you do have access to IID samples from each of their marginals. And then you want to learn a bijection f such that on samples xi drawn from the marginal of x, applying f will approximate the marginal of y. And similarly, on samples yi drawn from the marginal PDF of y, if we apply f inverse, we can approximate the marginal of x. Okay, so for domain alignment to be used for downscaling, we just need one of our domains x to be the coarse scale and one y to be the fine scale. This whole approach actually in align flow is completely symmetric, so you can kind of forget the denotation I had in the earlier slide that y would be the label. Here, these are just two different domains we want to align, and we could assign coarse or fine to either of them. I believe in the picture that we have of the architecture, we said that x is the coarse scale and y is the fine scale. So here are the assumptions. We assume we have IID access to samples from the marginal of x and separately to samples from the marginal of y. We don't assume we have access to the joint. That's essentially what we're trying to learn. And by making an assumption that x and y are conditionally independent, conditioned on z, which is a shared latent space, that would allow us to factor the joint as we have on the far right side. And then all we need to do to then basically learn a joint PDF over x and y is to learn the conditional PDFs x given the latent variable and y given the latent variable. And that'll be done using the align flow setup, and we'll talk about that in a second. I'll also say that since we're going to be learning a joint shared latent space, we have to start with some prior on that, but we can again just start with something really simple, just like in VAE. We can start with, say, an isotropic Gaussian, but unlike VAE, we can get to much more informative distributions over the latent space using normalizing flows than in, say, just a vanilla VAE. So I'll get to normalizing flows on the next slide. But the punchline for any practitioner is that, again, you don't need pairings between your examples from the two domains. So you don't need to know what is the corresponding fine-grained map of this spatiotemporal field corresponding to its coarse grain map. You just need independent samples from both. So normalizing flows came out in 2015, I believe, and the idea is you can take a very simple prior, like a simple Gaussian or uniform, and then you can compose a bunch of functions, these FIs, to get, these have to be invertible transformations, to get more informative distributions over the latent space. And then you just need to learn the parameters of those functions. And it allows you, so, when we relate either of our domains, the X domain or the Y domain, to our latent domain, we're going to learn a normalizing flow. We're not actually going to learn the normalizing flows of which I drew pictures here. We're going to use a different algorithm. So this is the architecture that Brian wrote down, which is essentially just the align flow architecture. It looks like that there's a lot going on, but really the only network parameters that are being learned are for these normalizing flows connecting each of our data domains to our shared latent domain. In particular, we use GLOW, which is based on one-by-one invertible convolutions by Kingma and Darwal. But the network parameters are going to be for those little FI transformations, getting an invertible transformation between X and the latent space, and then similarly for Y and the latent space. So that's where the network needs to learn parameters. Also, we're not going to do dimensionality reduction in the latent space. The latent space is just meant to provide this shared latent space over X and Y to align them in a joint PDF, which means that we're going to just use the same dimension of latent space as the dimension of Y, the high resolution data. And so for X, we have to get it into that dimension, but we do so in the simplest least information adding technique. It's an upsampling technique where we just look at neighboring pixels to populate the additional pixels without adding additional information. So all we can do when we're introducing generative downscaling, and it doesn't really exist in the literature, is compare to point-wise downscaling, and also those are mostly supervised methods. So we have an unsupervised generative method that we're comparing to some supervised methods. We're only comparing them on point predictions, which means these tables were generated with labeled data, so with paired data for the evaluation. So the top two methods were trained on paired data, and our method was trained on unpaired data, but they're all evaluated on paired data. BCSD is sort of the standard practice for downscaling. Banyo Medina was a paper that came out in Climate Informatics 2019 that was essentially using a CNN approach. And so, of course, we never consider an unsupervised learning method to outperform a supervised learning method, but we actually see it typically does outperform BCSD and is not that much worse than the CNN approach. But of course, now the limitations are the top two approaches can only be trained with paired data, and so they're limited by how much paired data they can be trained on. And also, they're only generating point predictions. So in my remaining, I guess, 3 minutes, I'll talk about the strengths of a generative downscaler. So we can, once we've trained our ClimAlign architecture, then we can test it as follows. We can send in a coarse-grained resolution temperature map coming from ERA. And this is, for the evaluation, this is actually a paired example where there is a fine-grained resolution temperature map that is paired with it, but the model does not see that. So I'm moving along the top row from left to right. So left is the input to query the model. Middle is the target that the model doesn't get to see. And then right in the gray shading is the maximum likelihood prediction from our ClimAlign model of the fine-grained resolution precipitation map. But we can also do both conditional or unconditional sampling from this model. So conditional sampling is conditioned on this input image at the upper left from ERA. We can sample a bunch of times from our latent distribution and then output fine-grained instances that are these 3 samples on the bottom. We could even do unconditional sampling where we don't even look at an input image such as ERA, and we just sample from the latent distribution. The other nice thing that you get in these types of models is the idea of latent space interpolation. So, and symmetry. So we can go from fine scale to coarse scale or coarse scale to fine scale. So in this particular example, on the top row, the extreme left and right images are actual images from WRF, from our numerical weather prediction model for precipitation. And then everything else is synthetic. And the way the synthetic images were generated is as follows. So we'll input, say, the image on the far right, we'll get our latent space representation. And then from there, that'll allow us to output the image on the far left bottom at coarse-grained resolution, and similar procedure for far right. Then we take the latent space representation from the far left and far right and just take a walk in latent space connecting these two, giving us these 3 latent space points in between, which then can generate images at both low resolution, so coarse resolution, the bottom row, and fine resolution, the top row. And this seems to be a plausible temporal interpolation between the points. I'm going to close. I'll mention that we're really interested also in machine learning for extreme events, like completely unsupervised learning approaches to learn multivariate extreme events of multiple types simultaneously. Hurricane track forecasting and hurricane intensity forecasting. Avalanche detection, we have an interesting VAE approach to that. and then various extreme events such as Indian summer monsoon precipitation. Thank you.
Thank you, Claire, for your nice presentation. So in the meantime, there are lots of questions that have appeared in our question box, and I'm trying to sort them. So there are a couple of technical questions and some more high-level questions. So the first one is a technical one. It says that typically the information that you have on the coarse grid is an average data. So you have some averaged mean over temperature, for example. So the variance of this coarse data is lower than the one you would have on the downscaled data. So how do you tackle this problem or take it into account?
That is a great point. Yeah, I don't have some good intuition on that. So we've certainly, in a lot of our other problems, anytime you have temporal data averaged over time segments, you reduce variance, or spatial data averaged over locations, you reduce variance. I'm thinking this is going to get encapsulated in the transformations that we learn to get to a shared latent space. And so it's one of those things that, the model is going to sort of compensate for that in the weights connecting the coarse grained domain to the latent space, and similarly the fine grained, but that is not going to give us a lot of intuition unless we go in and start visualizing the latent space, which is what most domain experts have been asking about when I've given this presentation. But it's a fair point.
Mm-hmm. And the next question is whether it's possible to combine the approach that you have with some of the background models that people would have, like if you work on weather prediction or so, there might be already some models out there that are known to work well, or like some background knowledge about the landscape of the place where you're working in. So I know this is a very difficult, or this is sort of one of the key problems in many fields of science, where you have machine learning on one side, but then there's lots of expert knowledge and you somehow don't really know how to combine the two things. So do you see any?
Well, that's a great point. So there's this emerging field of trying to constrain deep learning methods, which I think are typically supervised, right, with physical constraints. It's not a field that I've worked on, but I'm sort of following it a little bit. And I guess this question points to doing something similar in the field of unsupervised deep learning, or at least for the domain alignment task. So I think that speaks to some interesting future work, at least in the design of machine learning methods. But as of now, I'm not aware of something. Mm-hmm. That said, I got an interesting comment when I gave this talk earlier in the week, that if you look at something like this interpolation example, where from an AI perspective, we've just done a walk in latent space connecting two training images, and then we're claiming, oh, okay, since the two input images were at different times, then this can be interpreted as a temporal interpolation. Someone raised the point, well, look, you could run a bunch of NWP or other simulators to create like an ensemble of temporal interpolations and then compare them quantitatively here. So these are more sort of evaluation ideas that take into account our strength as, the community's strength as modelers, but not to get it directly baked in. I think that's still a pretty open area, although some people are working on it, at least in terms of supervised deep learning.
Mm-hmm. Okay, thanks. So the next question is whether or like in your talk, focused on one particular application, but he's asking what other spatial temporal processes might you be able to model with your approach, and whether you would need other ANN, like network architectures, to doing this, or whether you think that the architecture you currently use is pretty genuine for many tasks.
So yeah, I guess I have to just draw slightly a blank there and say that if you're an AI person in the audience, please get your scientific question from your domain expert. Don't try to just roll your own, as it were. So I think I'm not going to go too much out on a limb there. but maybe I'll use it as a second to mention my bonus slides, where we have done avalanche detection, and now we're using unsupervised deep learning to address the type of setting that might come up in a lot of examples, a lot of domains where you have severe class imbalance coupled with a severe limitation on the amount of data that you have as labeled data. So we wanted to do unsupervised learning as much as possible, and then use our labeled data only to tune a threshold on reconstruction error that we would use to treat the VAE as an anomaly detector. But yeah, I try to get my scientific problems from domain experts, and so I'm not going to shoot from the hip on that one.
Okay, no, that's fine. Then here's one by another geoscientist who works in our cluster by Bedata, and he asks about extreme events. So his question is whether extreme events are also reliably modeled in your downscaled outputs, and in particular, he's interested in precipitation.
Oh, okay, so interesting. I gave this talk at NCAR and had a domain expert say that, look, you know, ultimately your latent distribution is going to is not going to really represent your outliers, but we're in a field where we care about outliers because we care about extremes. So I think that could be a fair concern, I think, here too, in representing the latent space. But I think there would probably be a direct way to go at what you're talking about, which is to actually, with a domain expert, examine, maybe query some maps corresponding to extreme events and see how well we perform. And we haven't done that. One thing that you might be interested in that we have done is we've said, okay, we said we don't need our two domains to be coupled. Not only that, they don't even need to be generated by the same processes, right? We have WRF, which is NWP for one, and then we have reanalysis data, which is essentially smoothed observations as the other. We do have the alignment of the larger bounding box, but Brian did do one experiment where they were not temporally aligned. So we had coarse resolution from a different time period as our fine resolution data. And then when we trained from scratch with that setting, we still got good performance. Now the ultimate weights in the network to map to the latent space may change to make that alignment, but that was pretty nice that you were kind of robust to temporal gaps in the generation of your data at the two domains.
Mm-hmm. Okay, I have yet another one by a geoscientist. Sorry, I guess these are all really tough questions to a computer scientist, but anyway. So here's the next one. So in the setting where the core scale data is a distribution function for each cell. So for example, you have something like the temperature in the cell is between the range of X and Y. And now you want to get distinct values on this fine scale, whether this would work.
I think so. That would be pretty cool. Okay, but keep in mind, right, our setting here is really symmetric. So if you're saying that X now is a distribution over distributions, that's fine. But we still need IID access to Y. Now that could be a distribution over maps, a distribution over distributions of maps, but we do need IID access to the other domain. So you can't get something from nothing, right? Like, you know, now we have distributions over maps at one of the domains, but I couldn't tell from your question if we would also have IID access to the other domain.
Mm-hmm. Okay, thanks, Claire. I think we've now asked so many questions that maybe we should let you off the hook. So thanks for giving your presentation. So for tomorrow's, I'm just going to announce a couple of things for tomorrow. So this was the last talk for today. Tomorrow the conference goes on for one more afternoon, at least afternoon in our time zone. So we have talks by Manfred Klaassen, who's from the medical faculty in Tübingen, by Steffi Jegelka, who's at the MIT, Bedata Goswami, he's one of the persons who has just asked a question. He's one of the research group leaders in our cluster, and Igor Lesanovsky from the Department of Physics. So we're looking forward to yet another day of interesting talks. Stay with us, and for now, let's thank Claire again for this great presentation. I really enjoyed it. Thanks a lot, Claire, and see all of you tomorrow.
Okay, so we're not live anymore.